ሰላም ዛሬ የመጣሁት ሴሚስተሩ የመጨረሻ በሆነ ቪዲዮ ነው። ይህ ቪዲዮ በቤዚክ ማትማቲክስ ፋይናል ኤግዛም ሶሉሽን የያዘ ነው። ስለዚህ ሁሉንም ጥያቄዎች አንድ ባንድ ለማየት እንሞክራለን። Okay, the question is containing about this, simply it has 4 parts. The first part is true-false item, which contains 9 questions. Second item is multiple choice item containing 14 questions. The third part is blank space containing or simple, which has 8 questions, and the last part could be workout, which are 2. Then directly let us proceed to the first question of the first item, that is true-false item. And the question says, if f is a function defined from a to that of this one, that's simply b, is an odd function, then a range of f is equal to codomain of the given function. You know what range, codomain, and domain of a function? Here, if the function f is defined from a to b is said to be the codomain of the given function, and the domain of the given function is already the subset of this one, that's simply a, or itself, that is a, and the range could be the subset of its codomain, that is b. You know this fact. Then a function f which is defined from a to b is onto or simply surjective if every element of b is an element an element of b. There exists a which is an element of a, so that f of a is equal to b. That means the function, this function that is f, is surjective or simply onto if and only if each and every element of b, which is the codomain of this function, is an image for at least one element within the first set, that's simply set a. And therefore, this means every element b is mapped to b, mapped to by some element in a. That means it must be at least an image or simply for at least one element in a. Therefore, a range of f is equal to b, which is codomain of f. Hence, the given statement is that is true. That is true. That means if the function f from a to b is onto function or simply surjective, so that the range of the given function must be b, that is which is the codomain of the given function. So the first statement is true. Second one, if a is the subset of b, then intersection b is non-empty. A, the subset of b, that means each and every element of a is included in b. So that this implies that the intersection of these two sets is always different from that of non-empty. Then the statement is false. When we say this statement is false, let us take or simply counter example which support our answer. You know that as a counter example, if we take a to be an empty set and b to be the set containing these three elements, a can be empty set because empty set, we know that empty set is the subset of any set. So that in this case, the intersection of these two sets, whenever a is the subset of b, could be a intersection b could be empty set intersection the sets b containing 1, 2, and 3, so that their intersection would be empty sets, which contradicts our question. So that is why the answer for this statement is false. Question number 3. If a polynomial function p of x divided by x plus r, then p of r is the remainder. Remember the remainder theorem. Remainder theorem states that if a polynomial p of x divided by x minus c, then the remainder is always p of c. But what we are given here is x plus r, p of r. So that here x plus r is equal to x minus r. So that here, this one that simply c is minus r. Therefore, the remainder which is obtained by dividing the given polynomial p of x by x plus r, or x minus r, could be p of minus r. It is not p of r, so that here the answer is false. Next question, question number 4. If R is equal to the set containing an ordered pair of x, y such that y is equal to 2x minus 1, then R inverse is equal to yx, say that x is equal to y minus 1. And that this relation that the inverse is obtained, and the expected inverse of this relation is obtained from this one by applying two things. The first thing is the set of order pair xy is changed into yx. And x1 is the equation y is equal to x minus 1 could be converted into x equal to y minus 1, which is obtained by replacing x and y without solving for y. So that's the statement could be. But we know that to find the inverse of a relation, for our first step will be we have to swap or simply exchange x and y in the given equation that's simply here. So that when we do this, the original equation is y is equal to x minus 1 is given, so that when we exchange or simply swap x and y, we have x equal to y minus 1. And next we have to try to solve for y, that is the new y. And when we solve for this one, that's simply y for this equation, take this one to the left side and divide both sides by 2, then we'll obtain y is equal to x plus 1 over 2. Then the inverse of the given relation, that is our inverse could be, without changing the set order pair, that is xy, say that y is equal to x plus 1 over 2 could be exactly the inverse of this relation. But what we are given here is our inverse is equal to yx, x is equal to 2y minus 1. If we interchange y and that of x, we never change or simply swap the equation that is simply the variables x and that of y. Or if we interchange them, the variables or simply x and y, and solve for the new y, we never interchange the order pair, that is x, y should be kept as this. And therefore, the given statement is incorrectly write as x equal to y minus 1 without solving for y. Therefore, the statement is a false statement. Question number 5. The graph of a polynomial function with degree 3 has exactly 3 turning points. The graph of a polynomial function with degree 3 has exactly 3 turning points. We know that a polynomial of degree n has at most, that means the maximum number of turning points of the given polynomial function with degree n is n minus 1. So that it can be lower than that of n minus 1. So that, but what the given question said that if the degree is 3, it has exactly 3 turning points. But at most we will have, for simply the graph will have n minus 1 turning points. So that here for degree 3, the maximum turning point is 2. That is simply 2 n minus 1. That's 3 minus 1. Not exactly 3. For example, f of x equal to x cubed has no turning points. So that in this case, due to such a counterexample and due to the fact that a polynomial of degree n has at most n minus 1 turning points, the question will be false. Question number 6. If a is a rational number and b is an irrational number, then the sum a plus b is irrational. Sum of rational and irrational number is irrational always. A proof by contradiction. Suppose a plus b is equal r is rational. In order to prove, by using that proof by contradiction, suppose that a plus b is equal to r. This one, that is r, is a rational number. Then if it is a rational number, b is equal to r minus a must be rational minus rational, which is equal to rational. But what we are given here is b is irrational number. So that's this is a contradiction, since b is irrational. Therefore, the answer could be true. That means the sum of any rational and irrational number is always irrational number. Question number 7. The graph of a polynomial function may not have y-intercept. The graph of a polynomial function may not have y-intercept. We know that the y-intercept is found by evaluating or simply by letting x to be 0, so that since the domain of every polynomial function is the set of real number, so that there is also included within the domain of the given polynomial function, so that when we substitute 0 for x, we'll obtain a certain value, which is the expected y-intercept of the function, that is the polynomial function. Therefore, every polynomial is defined for all real numbers, including x equal to 0. So f of 0 is always exists, which always has a y-intercept. So it could be at the origin, or that is, the y-intercept could be the origin, or it may be on the positive y-axis or simply negative y-axis, so that whatever it is, the polynomial function has always y-intercept, so that it is false. Question number 8. Let A is different from that of empty set, and A the subset of R. If set A has a lower bound, then it has a greatest lower bound. A is an empty set, A the subset of real number. If A has a lower bound, that is, which are elements less than that of every element of the given set there, then it has a greatest lower bound. By using that of completeness theorem, or simply completeness axiom of real number R, every non-empty subset of R that is bounded below has the greatest lower bound, or simply MPMM. So what we are asked, or simply what we are informed here is A is non-empty, A is a subset of R, and it has lower bound that's simply bounded from below. Therefore, a given set A is non-empty and has a lower bound. Then by completeness axiom, which already state here, A has greatest lower bound. So the answer is true. That means every set, if every subset of set of real number, if it has a lower bound, it must have a greater lower bound, and if it has even an upper bound, it must have least upper bound. And that is why this is true. Next question, question number 9. If f of x is equal to 1 minus 2x over 3x plus 6, then the horizontal asymptote of f is y is equal to 1 over 3. Remember that for a given rational function to have a horizontal asymptote, either the degree of the numerator and the denominator must be equal, or the degree of the numerator should be strictly less than that of the degree of the denominator. When the degree of the numerator is strictly less than that of the degree of the denominator, so that the x-axis, or simply the line y is equal to 0, will be the horizontal asymptote. But when the degree of the numerator is exactly equal with that of the degree of the denominator, so that the line which passes through the quotient of the leading coefficients of the numerator and the denominator could be considered as it is horizontal asymptotes. Then for a fraction, that means for a fraction, for a rational function, f of x equal to x the power of n plus the other terms divided by b times x the power of m. Then we have if the degree of the numerator is equal to degree of the denominator, which is equal to, for example, 1, the horizontal asymptote could be y is equal to a over b. So that in this case, here, a is minus 2, b is minus 3. That is, the leading coefficient of the denominator is minus 2, and the leading coefficient of the denominator is 3, so that the horizontal asymptote could be y is equal to the numerator, the leading coefficient of the numerator, which is minus 2, divided by the leading coefficient of the denominator 3, which is minus 2 over 3. It is not 1 over 3, so that the given statement is automatically false. Okay, this is all what about the first part of the question, and the next part could be part 2, the first question could be this one, that is, let f is equal to the set containing 2, 3, 4, 9, 3 minus 8, and 5, 1, and let second function g is containing 1, 2, 2, 5, 3, 0, and 4 minus 1. Then we are asked just to find f times g. Then, by definition, we know that f times g of x means, I think it is not a compulsion, rather it is an operation which is the product of two. And it is not a composition, rather just the usual multiplication of functions, so that in this case, we have f of x, f times g of x means f of x times g of x on a common domain. That means for this operation to be practicable, f and g have non-empty common domains. I'm sorry. And non-empty common domains, and therefore the domain of G, as it is given here, the domain of G could be the set containing 1, 2, 3. Sorry, the domain of G, I mean, the G is this one, so that 1, 2, 3, and 4. And range of G, that is 2, 5, 0, and minus 1. Similarly, the domain of the first function, that's simply f, could be 2, 4, 3, and 5, and its range could be 3, 9, minus 8, and 1. So let us take the common domain here, the intersection of the domain of G and F, or simply F and G. The common domain, or simply their intersection, the set containing 2, 3, and 4. That is, we have 2 here, we have also 2 here, 3, 3, 4, 4. And then let us compute, or simply the products at x equal to 2. That is the first element of the intersection of the domain of f and g. F of 2 is the image of f, and the image of 2 under f is 3. And the image of 2 under g is 5. So that their product will be, that is 3 times 5 could be 15. Similarly, at the second intersection point, that's simply 3. The image of 3 under f is minus 8, we have here. And the image of 3 under g could be this one, that's simply 0, so that their product, which is minus 8 times 0, is 0. And last 3 at 4, the image of 4 under f is 9, and the image of 4 under g is minus 1. That is 4, 9, 4 minus 1, so that their product will be minus 9. Therefore, so the product f times g could be the set containing the element that's simply 215, the image of 2, which is a product of the images of f, I mean 2 under f and that of g, which is 15. For 3, it is 0, and 4, it is already this one, that's simply minus 9, to that. The answer could be, that is C. The answer is C. Okay, so, sorry, we didn't write the alternatives here. Anyways, the answer is C. Question number 2. Which of the following is not a polynomial function? We have these 4 alternatives. A, the function f of x equal to x squared minus 5. B, g of x equal to the square root of x the power of 4 plus 2x squared plus 1. C, f of x equal to the absolute value of x squared plus 1. And D, it is already named. And then we know that a polynomial is the sum of terms, or simply the terms must be written, or simply it must have of this form, that is n times the power of n whenever n is any non-negative integer end. This one that is n, that is the coefficient of the term, could be any real number. And then a polynomial, a coefficient -5 minus pi min. That means for a, actually -5 is a constant, minus pi is a constant term, and the leading coefficient is 1, and the exponent here is 2, so that it can satisfy the definition to be a polynomial function. So that, without any doubt, f of x equal to x squared minus 5 minus pi is polynomial function, which is quadratic. Similarly, for b, we have the square root of x to the power of 4 plus 2x squared plus 1, which can be further simplified too, but since this one is perfect trinomial, it is x squared plus 1, the whole square, so that this square can cancel the square root, and we can obtain the absolute value of x squared plus 1. But we know that this one, that's simply the term which is within this absolute value, that is x squared plus 1, is positive real number for every x, or simply for any real number, so that it could be that is the simplified form of this one, that is the square root of x to the power of 4 plus 2x squared plus 1 could be x squared plus 1, which is already positive. And there is also a polynomial function. And C, that is the absolute value of x squared plus 1, which is identical with B. Since it is absolute value of x squared plus 1, it is also a polynomial function. So all are polynomials. So that the answer must be D. That means there is no any expression which is not a polynomial function. Therefore, the answer for this one would be D. That is all A, and that is f of x, g of x, and again f of x. That's simply all the three given expressions are polynomial functions. Question number 3. The degree of the polynomial function x squared minus 1 times x plus 1 minus x cubed plus 2x plus 1 is A3, B2, C1, D9. So in order to have the, just to know the degree of the product of this polynomial function, we have to further write it in the form of that of the standard form of a polynomial function. Then when we expand x squared minus 1 times x plus 3, it's already x cubed plus x squared minus x minus 1. And then x cubed plus x squared minus x minus 1 minus the given here, that is minus x cubed plus 2x plus 1. Could be, that is x cubed minus x squared could be cancelled. So what's left here is only x squared plus minus x plus 2x. Collecting like terms, that means plus minus 1 plus 1. So that could be x squared plus x. X squared plus x, that means minus 1 plus 1 is 0, minus x plus 2x is already x. We have x squared here, so that x squared plus x could be the simplified form of this given expression. Therefore, if it is equivalent to that of x squared plus x, so that the degree of the given polynomial function will be that the exponent of the term, which with the highest exponent of the term, this one, that's simply 2. Therefore, the answer for this one could be this one, which is B. Question number 4. Which of the following is false? A, every one-to-one function is an onto function. B, there are functions which are neither one-to-one nor onto. C, any function is a relation. D, none. So let us see this one. A is false because being one-to-one or simply injective doesn't imply that's surjectivity or simply onto. And an example, if a function f is defined from R to R, f of x equal to e the power of x is injective, that is simply one-to-one for each and every x. We have a specific or simply unique image for each and every real number, that is R. And this is an injective or simply one-to-one function, but it's not onto. For this function to be an onto, each and every real number must be an image for at least one element within the expected domain of this function that is f, that is set of real number. But we know that this function that is f of x can never be negative for any real number, or simply there is no any real number which can make this one that is f of x to be negative. That means these real numbers, or simply negative real numbers, are not an image for any element of the domain of the given function, so that this function is not an owned function. If the function is defined from R to R, that means. So that due to this fact, this one that is A, that is every one-to-one function, is an owned function, is a false statement. B is true, that means there are functions which are neither one-to-one nor onto. And so basically, we may have a function which is one-to-one, or simply neither of these two, that is one-to-one nor onto function, so that it's true. C is also true, that is any function is a relation. We know that function is a special type of a relation, therefore every function can be a relation, but every relation may not satisfy a condition to be a function. So that is true. Then what we are asked here is, we are asked just to select a false statement, therefore the false statement is, here is A. Okay, question number 5. The complex number z is equal to 2 minus I over 1 plus I lies on, that is the quadrant. That means in order to specifically the quadrant, we must know the imaginary and the real part of the given complex number. To do that, we have to simplify first, or simply change this one in standard form. Then first simplify, multiply the numerator and the denominator, both the denominator and the denominator of this one, that simply z, by the complex conjugate of the denominator, which is minus 1 minus I. When we do this, z becomes 2 minus I times the complex conjugate of the denominator, which is 1 minus I, divided by the product of 1 plus I and its complex conjugate, which is minus 1 minus I. So that will have 2 minus 2I minus I plus I square over 1 minus I square, which is equal to, that is 2 minus 3I minus 1 minus 1, here is, that is the square of minus I is minus 1 over 1 plus 1, that's simply 2, which is 1 over 2 minus 3 over 2. Therefore, the real part of this complex number, that's it, is positive, and its imaginary part is minus 3 over 2, which is negative, so that whenever the first coordinate is positive and second coordinate is negative, this will be the property of the, I think, the fourth quadrant, so that the complex number lies in the fourth quadrant, therefore the answer is D. Question number 6. Which of the following function is not one-to-one function? A, f of x is equal to x squared on 0 to 5, f of x is equal to x squared on negative 5 to 0, f of x is equal to x squared on minus 5 to 5, and D none. So we have to remember the definition of what the criteria for a given function to be one-to-one. We know that f of x equal to x squared is one-to-one on the given interval whenever where it is a strictly monotonic function. Or it's an increasing function, or simply monotonically decreasing function. That means, so that on 0, 5, it is an increasing function, so that each and every element of this interval will have a unique image, so that it is one-to-one function. Similarly, B is a decreasing function. That means whenever x is increasing, its functional value will also decreases, so that here it is also one-to-one, since it is monotonic. But this one, that's simply the same function on the interval minus 5 to 5, it is not one-to-one, because f of a is equal to f of minus a, for a different from that of 0, so that two different elements of that interval, that's the domain of this function, may have has the same image, so that due to this fact, the function that is f of x equal to x squared on this interval that's minus 5 to 5 cannot be one-to-one function. So that the function which is not one-to-one could be this one that simply c, so that the answer could be and that is c. This is a counter example, that is f of 2 is 4, f of minus 2 is also 4, so that due to the identicality of this one that's simply 4, which is the image of 2 and that of minus 2, which are different, so that the function is not a one-to-one function. Question number 7. Which of the following pairs of function is an inverse of each other in their respective domain? Here, a is given to be f of x equal to the square root of x plus 3, and g of x is x squared minus 9. F of x equal to x cubed minus 1, and g of x equal to the cube root of x plus 1. Okay, I think two alternatives are remained. Let us check for B. B, that is f of g of x f of g of x could be the cube root of x plus 1 minus 1 is equal to x plus 1 minus 1 is equal to x. That means what I need to apply, the concept that I need to apply here is that, for example, if the given function that is f and g are, one is the inverse of the other, so that the composition function that is f composite of g of x must be x, or g of f of x or g composite of f of x must be x. That is the criteria that I need to apply here. So that for B, if we assume that f of x equal to x cubed minus 1 is the inverse for g of x equal to the cube root of x plus 1, so that the compulsion f composite of g or g composite of f must be g composite of x must be x. So that when we do this, f composite of g of x equal to the cube root of the cube of the cube root of x plus 1, that's simply g of x here, and minus 1, we have minus 1 here, so that the cube of the cube root of this one is x plus 1 minus 1 is equal to x, so that exactly f of x, which is equal to x cubed minus 1, is the inverse of the cube root of x plus 1. And also when we commit them together, g composite of f of x equal to the cube root of x cubed minus 1 plus 1, which is equal to the cube root of x cubed, which is equal to x. That is minus 1 plus 1 is already there. That means so that domain of R, domain or range, much that is f to R to R, g is also R to R. Therefore, the function that simply this one is that is f is the inverse of the given function that's simply g of x. In order to check A, f composite of g of x is equal to f of x is x, the square root of x plus 3, and g of x is x squared minus 9, so that there is already f of g of x is x squared minus 9, the square root of x squared minus 9 plus 3, which is the square root of x squared minus 6, which is not exactly equal with that of x. So that due to this, we can imply that x squared minus 9 cannot be the inverse of the square root of x plus 3, or the square root of x plus 3 cannot be the inverse function for x squared minus 9. So that also the domain issue is f requires x greater than or equal to minus 3, and g, the output, can be less than that of minus 3, so that due to this, this one that is f of x, which is equal to the square root of x plus 3, cannot be the inverse of g of x equal to x squared minus 9, or vice versa. Therefore, the answer for this question will be, that is B. Question number 8. Consider f the function that is f containing these elements and g with its corresponding elements. Then 2 times f plus f over g of 2 is blank. A minus 1, b minus 3, c1, and d 0. So a combination could be, we know that 2 times f plus f over g of 2 is equal to 2 times f of 2 plus f of 2 over g of 2. Correctly? Because 2 times f plus g, f plus f over g of x is equal to 2 times f of x plus f of x over g of x already. Whenever x is 2, f2 times f plus f over g of 2 is equal to 2 times f of 2 plus f over 2 over g of 2. Then from status, f of 2 is given to be, within this one, f of 2 is minus 1. We have to, and g of 2 could be, we have 2, that's simply 1, so that g of 2 is 1. Therefore, when we substitute this one in the formula, that's simply here, we have 2 times minus 1, that is 2 times f of 2, plus minus 1 over 1, that is simply f of 2 over g of 2, which is f of 2 is minus 1, so that we have minus 2 plus minus 1, which is equal to minus 3. So that the alternative containing minus 3 could be this one, that's simply B. Therefore, the answer is B. Okay, question number 9. If z is equal to z, if z plus z bar is equal to 10, then the real part of z is a5, b10, c0, and d5, negative 5, I mean. So in order to know the real and imaginary part of this equation, that is z plus z bar is equal to 10, we have to first write or simply know the standard form of z. To do this, we have to simplify first z. So we can start by letting z is equal to, in standard form, that is a plus pi. Then it is a complex conjugate that z bar could be a minus pi. Then z plus z bar could be a plus pi, because we are letting z to be a plus pi, plus z bar, which is a minus pi, which is equal to a, which is equal to 10. That means pi plus minus pi could be this one, that's simply 0, and we have a plus I mean a plus a, which is equal to a, and the equivalent with this one, that's simply 10, so that a is equal to 10. We know that the sum of every complex number and its complex conjugate is always twice of its real parts. So that it is 2 is equal to 10, and then is equal to 5. Dividing both sides by 5, we have, by 2, we have is equal to 5, so that the real part could be, it is purely real, which is 5. Therefore, the correct choice for this one could be A. Question number 10. Which of the following is not true? A, the range of every polynomial function is not bounded. B, a vertical asymptote indicates how the graph of a rational function behaves near infinity. C, for a rational function f, if f of a is equal to 0, then the line x equal to a is said to be a vertical asymptote of f. And D, all of the above. That is, all of the above are not true. That means, so A is false. That is, the range of every polynomial function is not bounded. Is false. That means some polynomial functions have bounded ranges. Example, constant functions. Constant functions. So that the range of every polynomial function may not be set of real number. So just as a counter example, constant function, the range is the constant itself, that is a singleton, and therefore it is bounded. Therefore, the statement the range of every polynomial function is not bounded is false, because it can be bounded. That means B is also false. A vertical asymptote indicates how the graph of a rational function behaves near infinity. A vertical asymptote shows behavior near a finite x value, near a finite x value, not near infinity. That means a vertical asymptote is a vertical line which passes through a certain value of x, so that the vertical asymptote behaves the behavior of the given function near to that real number that is x, where the vertical asymptote is passing through to that. It is not near infinity, therefore, that is why this one, that simply B, is false. C is also false. That means if f is equal to a, maybe 0, not necessarily vertical asymptote, because if it is simplified, or simply if there is a factor that can cancel x minus a from the numerator of the given rational function, so that x equal to a may not be necessarily vertical asymptote, rather it may be a whole. And that means a vertical asymptote occurs whenever the denominator that's simply is 0, but the numerator is non-zero at that point. That is, if x is equal to a is a vertical asymptote, the denominator must be 0 at a, but the numerator must be non-zero. So that all statements A, B, and C are false. Therefore, D, all of the above statements are not true. Is the answer. Question number 11. Which of the following the range of f is equal to x plus 2 over x minus 2? Range of rational function. A, R without a set containing 2. B, R without a set containing minus 2. C, R without a set containing minus 1. And D, R without the set containing positive 1. Let y is equal to x plus 2 over x minus 2. Then let's try to solve for x. Then y into x minus 2 is equal to x plus 2. This implies yx minus 2y is equal to x plus 2. So that we have yx minus x equal to 2y plus 2, which implies x into y minus 1 is equal to 2 into y plus 2. Then x equal to 2 into y plus 1 over y minus 1. So the domain of this function that's in terms of y could be the range of this expression. So that x equal to 2y plus 1. So that this function will be defined only when y is different from that y, simply y is equal to 1. Therefore, the range of this function, or the domain of this one in terms of y, could be set containing or real number without 1. Therefore, x exists if y different from that of 1. So that denominator is then 0. So the range could be all real numbers except y is equal to 1. That is r without positive 1. Therefore, the answer is this one. That's simply D. Question number 12 is about this graph. Which statement is true about the graph shown here? A, the degree is odd. B, the leading coefficient is negative. The constant term is 150 and has 4 distinct roots. Okay. For A, the first one, the graph shows it is in this directed upward direction. So that automatically the degree is even. If the degree is odd, the degree of the given function is odd, so that the ends of the given function must be in opposite direction. One tends to the upward direction, and second end will be directed down. So that the first one is false. B, as x approaches infinity, y also tends to positive infinity. So that the leading coefficient is positive, that means. So that B is also false. And that means the leading coefficient is negative is false. That means because since it is negative, the property is positive. C, the constant term is P of y, that is the y-intercept. The graph shows y is approximately That means simply the y-intercept is this one, that is the point at which the graph of the given function crosses the vertical axis. It is just below the x-axis, which is approximately negative infinity, negative 150. It is not positive 150, so that C is also false. Next, the graph crosses the x-axis at 4 points. Here we have 1, 2, in between -2 and 0, 1. We have also here in between 2 and 4, and in between 4 and 6. So that here the 4 distinct real roots. That means we know that the root of a polynomial function means at the point at which, that's simply graphically, at which the graph crosses or simply touches the horizontal axis or simply the x-axis, so that the graph touches or simply intersects the horizontal axis at 4 distinct roots, points, so that there is already the graph, the function has 4 distinct roots. Therefore, the answer is D. Question number 13. Which interval contains a 0 of f of x equal to 3x to the power of 4 minus 9x cubed plus 3x squared minus 6? The alternatives are given here. Then in order to use this one, or simply just to answer this question, we have to use or simply apply intermediate value theorem or simply location theorem. Using intermediate value theorem or location theorem, we have to check the sign change that f will have a root on the interval that is AB if f of a times f of b is negative. That means either then that is whenever the functional values or simply the sign of the functional values at a and b are opposite. That is either the first is positive and second is negative, or the first is negative and the second one is positive. So that this will be an indication for the existence of at least one root for the given function within the given interval that is AB. Therefore, the computation could be for the first one, f of 2, if you substitute 2 in the place of x here, we have minus 8, which is negative, and b, that's simply 3. F of 3 will be this one, that's simply 21. As we clearly observe here, the sign of f of 2 is negative and f of 3 is positive, so that their product is negative. Therefore, it can satisfy this one, that's intermediate value theorem. So the function, that same function will have a 0 in between 2 and that of 3. But for the second one, that's simply, for example, over this one, that the root 1, f of 0 is negative 6, and f of 1 is negative 9. So product can never be negative, so that the function will never have any root on this, or simply in the interval, or simply in between 0 and 1. So that we can check also the other alternatives, so that sign changes will be existing in between f of 2 and that of f of 3, so that f has 0 in the interval 2 to 3, that is in between 2 and 3. So that the answer for this question could be, that is A. I think the last question for this part. Which function might have the graph, the given graph? We have the graph here pictorially, and we're asked just to select which rational function is suitable for the graph of this function. Okay, the graph shows a vertical asymptote. The vertical asymptotes are at x equal to -2 and x equal to 3. So that this could be, when we measure only this one, A can be, the vertical asymptote of A could be, that is x equal to -3, -2 and positive 3. It can even C, the same vertical asymptote, but this one, that simply B, cannot be the graph of this function, because the vertical asymptote for this one could be x equal to 2 and x equal to -3. Okay, but the others could be, there is a possibility, but let's check. 0 at x equal to 2, that means simply a graph intersected the horizontal axis at 2 here, approximately at 2, that means. And the next one, that's simply as x approaches infinity, y tends to, that is positive infinity, y tends to positive, 0 from the positive part. That means when we measure that simply, the limit of the function that is near the vertical asymptote x equal to 3, whenever x tends to that of positive 3 from the right side, it goes in the upward direction, that's simply positive infinity. But when x approaches that of very large positive number, y approaches the horizontal axis from above. That is y from the above, that's simply in the plus sign. And when x approaches negative to from the left side, here, the curve or the graph, the given function indicators, y tends to negative infinity. And as x approaches negative to from the right side, from this part, the graph goes in the upward direction like this, so that y tends to positive infinity. Similarly, as x approaches 3 from the left side, from this side, the graph tends to the positive infinity. And from the right side, from the left side, as x approaches 3 from the right side, y tends to, sorry, it is not positive, rather it must be negative infinity. This negative infinity is not positive. And negative infinity, therefore the property, so that this property could be the property which is satisfied by the first one. That is, the vertical asymptote for this function is x equal to negative 2, which is the 0 of the denominator, and x equal to positive 3. And the 0 of the given function is, that means the x-intercept, that is whenever this point is 0, this is already 0, that is x equal to 0, that is x equal to 2 could be it is 0, that is the x-intercept. And the limits and other property will be satisfied by this graph, so that this could be the answer for the given question. But for example, that is simply with respect to that of the vertical asymptotes for alternative C, there is also that is simply the x-intercepts are the same. But the limits are, because there is positive 2, that is the square, there is also square, so that the limits can never be negative infinity. That is, for example, the limit of this function whenever x approaches 3 from the right side, from the left side, whatever it is, either from the right or simply from the left side, so that y should tend this to negative infinity. Sorry. I made a mistake here. That is the limit of this function. That's simply this one. When x approaches 3 from the left side is already negative infinity. That is simply from this one. And from the right side, it is exactly the same. That is positive infinity. Positive infinity. So that as it is written, it is already correct. So then, anyways, the answer is E. Okay, thank you. That's all.